Some things that align perfectly do so by chance. For example, Mark Twain was born on the day that Halley's Comet appeared in 1835 and died on the day it reappeared in 1910. However, when you consider the universe, everything in it seems so perfect. As if there had been a plan for human existence from the very beginning. With the high improbability of every single detail falling perfectly into place, many people have wondered why the universe seems so perfectly tuned. Well, in this video we explore why the universe is so perfect. We might take our body for granted because it's always there and always responds when we need it. However, have you paused to consider the marvel that the human body is? For instance, how come your body is perfectly suited for balancing and walking on two small parts called feet? The answer lies in a remarkable web of coordinated systems, voluntary and reflexive, neural, muscular, and skeletal, that allows us to walk down a sidewalk or run down a forest path largely without thinking. We may take these systems for granted, but they are a breathtaking testament to nature's engineering power. Our forefathers were quadrupeds, meaning they walked on four legs. Scholars debate when and why transformations began in our ancestors' quadrupedal body plan, resulting in our bipedal body plan over millions of years. That is, you and I and our ability to walk naturally on 2 feet, which is unique among the Earth's 200-plus primate species. It is basically like trying to make a table that balances on 2 legs. While it is technically possible, it is such a waste of time and may not even add any value, so nobody bothers with it. In fact, when we compare our forward motion to that of quadrupeds like chimps or gorillas, we've got the worst of both worlds. We not only have 2 legs, but our center of gravity is much higher off the ground, just above our waist, making us naturally tippy. You could say the deck isn't stacked in our favor. Well, for starters, our ancestors, the hominins, creatures more closely related to us than other apes, evolved into columns. Everything in us humans is in alignment, just like in a weight-bearing column, from our skull down through our spine and pelvis to our legs and feet. Gravity is essentially pulling straight down the column so we can stand and walk very efficiently. This makes a huge difference in terms of upright posture and travel. Consider how you'd feel if you tried to walk like a chimp bent over forwards. You could probably spend the entire day bent forward like that. However, your back muscles will be sore and you'll be unable to walk for the next 2 days. To achieve this verticality, our forefathers' quadruped skeletons were modified. Most experts agree that the pelvis was the most significant change in bipedalism. In fact, the pelvis is what truly distinguishes us from other members of the human family. A typical quadruped's pelvis, such as that of a gorilla, is long and slanted forward. Ours is short, squat, and perhaps most importantly, vertical, a completely different type of organism. All of the other differences that aided upright posture were primarily concerned with keeping everything in the same plane, that is, columnar. The foramen magnum, which connects the brain to the spinal cord, for example, migrated from the back of the skull to the bottom. The spinal column shifted from horizontal to vertical. The S-shaped curves in our spine were required to keep our forward-weighted head and trunk balanced over our pelvis and legs. Our femurs or upper leg bones angled inward toward our knees, while our shin bones became perpendicular to our feet. Finally, our toe bones are shortened and flattened, and our big toe aligns with its 4 companions. All of which are ideal for bipedal walking on the ground. But that is not the condition that makes bipedal walking possible. There is another important component known as the muscle. Indeed, bipedalism reveals significant differences in all 3 major upper leg muscles shared by all primates: the large, medium, and small gluteal muscles. The medium and small gluteals in chimps help to extend the trunk, allowing them to run and climb. The large gluteal muscle, gluteus maximus, serves this function in humans. We use our butt muscles, our body's largest, whenever we climb stairs or run along a forest path. Meanwhile, our medium and small gluteals are abductors, muscles that move our legs away from our body's central axis. Think of feet together as opposed to feet apart. The purpose of the abductors is to keep the body from falling over to one side when standing on one leg. Chimps and other primates lack this ability, and if they tried to stand on one leg, they would fall over. Bet you never thought of that. But there is one more thing that makes this incredible alignment of the human body for walking possible: taking instructions. Of course, without instructions, your muscles do nothing. These are delivered through your neural networks, the impossibly intricate network of nerves that run up our spinal cord and into our brain. Surprisingly, some instructions are sent entirely through the spinal cord. In fact, scientists say a lot of fundamental movements never make it to your brain. For example, a runner does not have to tell her legs what to do every time she takes a step because basic reflexes tell the legs what to do every time. Such movements not only happen without a second thought, but also without a first thought. When you are moving, however, the story changes. You rely on your brain to voluntarily override or modify those reflexes in order to avoid obstacles like the exposed route you didn't see. At any given time while walking or running, our brain is coordinating the movements of hundreds of muscles throughout our body. It is not only the muscles of the legs and feet that help stabilize us during forward movement, but also those of the torso, shoulders, arms, and neck. Now, there are three major sources of information on your body's location in space, potential hazards, and so on that feed into your brain. Your eyes are one of them. Another type of nerve cell is the proprioceptor, which detects positional changes in our muscles and joints. Finally, there's our vestibular system, the remarkable balancing apparatus in your inner ear. How come all these parts come together so nicely and efficiently that we can so easily walk? And yet, when you look into the universe, you quickly become overwhelmed by other coincidences that are even more troubling when you think about them. Physics has discovered basic features of the universe that appear to be lucky accidents at first glance over the last several decades. Theories now suggest the most general structural element of the universe, stars and planets, as well as the galaxies that contain them, are the result of finely tuned laws and conditions that appear too good to be true. What if the only satisfying answer to our most fundamental questions, our late-night musings about why we're here, is an exasperated shrug and a meekly muttered, "Things just seem to have turned out that way"? But do things always have to turn out that way? It can be unsettling to consider the unlikely nature of your own existence, to work backward causally and discover the chain of blind luck that brought you to your computer screen, your mobile device, or wherever you are watching this video. Your parents had to meet for you to exist at all, which required a lot of luck and coincidence. If your mother hadn't decided to take that calculus class, or if her parents hadn't chosen to live in another town, your parents might never have met. And that is just the tip of the iceberg. Even if your parents made a conscious decision to have a child, the chances of your specific sperm finding your specific egg are 1 in several billion. And the same is true for both of your parents who had to exist in order for you to exist. And so we are already down to 1 chance in 10 raised to the power of 27 after only 2 generations. Continuing in this manner, your chances of survival were almost infinitesimally small, given the general state of the universe even a few centuries ago. You and every other human being are the products of chance, and we came into being against all odds. And just as your own existence appears to have been wildly unlikely from a physical standpoint, the existence of the entire human species appears to have been a matter of blind luck. In 1994, Stephen Jay Gould argued that the detailed path of evolution is as random as the path of a single sperm cell to an egg. Evolutionary processes do not favor Homo sapiens or even mammals. rerun history with only a minor change and the biological outcome could have been drastically different. For example, if an asteroid hadn't hit the Yucatan 66 million years ago, dinosaurs would still be roaming the Earth. And humans would not have evolved according to scientists. It can be emotionally difficult to accept humanity's radical contingency, especially if you've been culturally conditioned by the biblical creation story, which portrays humans as the reason for the entire physical universe, designated as lords of a single, central, designed, habitable region. In the 16th century, Nicholas Copernicus upended this picture by moving the Earth slightly off-center, and every subsequent advance in our understanding of cosmic geography has bolstered this view that the Earth holds no special place in the grand scheme of things. The notion that billions of visible galaxies, let alone the vast expanses we can't see, exist solely for our benefit is patently absurd. Of course, scientific cosmology has consigned that notion to the dustbin of history, although it has not been able to answer all the questions that have come up. As difficult as it is to accept, you can rest assured that you are an accident, as is humanity. But what about the universe as a whole? Can it be that galaxies exist by chance, or that nuclear reactions inside stars eventually produce the chemical building blocks of life from hydrogen and helium? Some theories postulate that the processes underlying these phenomena are dependent on finely calibrated initial conditions or unlikely coincidences involving natural constants. One could always attribute them to chance, but many cosmologists have found that unsatisfying and have sought physical mechanisms that could produce life under a wide range of conditions. Cosmologists have embraced a general theory of the history of the visible universe since the 1920s, when Edwin Hubble discovered that all visible galaxies are receding from one another. According to this theory, the visible universe arose from an unimaginably compact and hot state. Prior to 1980, standard Big Bang models predicted that the universe expanded and cooled at a constant rate from the beginning of time to the present. These models were adjusted to fit observed data by choosing initial conditions, but some were concerned about how precise and unique those initial conditions had to be. Big Bang models, for example, attribute an energy density, the amount of energy per cubic centimeter, to the universe's initial state, as well as an initial rate of expansion of space itself. The subsequent evolution of the universe is highly dependent on the relationship between energy density and rate of expansion. Pack the energy too densely, and the universe will eventually recontract into a big crunch. Spread it out too thin, and the universe will continue to expand indefinitely, with matter diluting so quickly that stars and galaxies cannot form. Between these two extremes is a highly specialized history in which the universe never contracts and eventually slows to zero. This unique situation is known as W equals 1 in cosmological parlance. Cosmological observations show that the value of W for the visible universe is currently close to 1. This is a surprising finding in and of itself, but the original Big Bang models tell us that W equals 1 is an unstable equilibrium point, similar to a marble perfectly balanced on an overturned bowl. If the marble is exactly at the top, it will stay there, but if it's even slightly displaced from the very top, it will rapidly roll away from that special state. This is an illustration of the cosmological fine-tuning. This particular initial condition had to be just right at the start for the standard Big Bang model to produce a universe even vaguely similar to ours now. Some cosmologists were skeptical of this idea. It was possible that our solar system formed by chance and that life evolved on Earth. But it seemed unlikely that the entire observable universe began so close to the critical energy density required for cosmic structure to exist at all. And that isn't the only fine-tuned initial condition implied by the original Big Bang theory. If you train a radio telescope at any region of the sky, you observe a cosmic background radiation, the so-called afterglow of the Big Bang. The strange thing about this radiation is that its temperature is quite uniform no matter where you measure it. One might suspect that this uniformity is the result of a shared history and that the various regions must have descended from the same source, but they don't according to the standard Big Bang models. The radiation can be traced back to completely disconnected parts of the universe's initial state. Temperature uniformity would have had to exist in the initial state of the Big Bang, and while this initial condition was certainly possible, many cosmologists believe it is highly implausible. Alan Guth, an American cosmologist, proposed a different scenario of the early universe in 1980, one that reduced the need for special initial conditions in accounting for the uniformity of background radiation and the energy density of the universe we see today. Guth coined the term inflation to describe a brief period of hyperexponential expansion of the universe that occurred shortly after the Big Bang. This enormous increase in size would tend to flatten the universe, driving W very close to 1 regardless of what it had previously been, and would imply that the regions from which all visible background radiation originated did in fact share a common history. At first glance, the inflationary scenario appears to solve the fine-tuning problem. We can make the current state less sensitive to precise initial conditions by changing our story about how the universe evolved. But there are still reasons to be concerned because inflation cannot simply be wished into existence. We must postulate a physical mechanism that drives it. Early attempts to devise such a mechanism were motivated by the realization that certain types of fields, specifically the hypothesized Higgs field, would naturally produce inflation. However, more precise calculations revealed that the type of inflation caused by this Higgs field would not result in the universe we see today. So cosmologists cut the Gordian knot. Rather than looking for the source of the inflation in a field already postulated for another reason, they simply assumed a new field, the inflaton field, with exactly the properties required to produce the phenomena. Unfortunately, the phenomena to be explained, which include not only the current energy density and background radiation, but also the formation and clustering of galaxies and stars, necessitate a specific form of inflation. As a result of this slow-roll inflation, the form of the inflation field is severely constrained. The constraints are so severe that some cosmologists are concerned that one type of fine-tuning, exact initial conditions in the original Big Bang theory, has simply been traded for another, the precise details of the inflaton field. However, the inflationary scenario matches the precise temperature fluctuations of the background radiation so well that an inflationary epoch is now an accepted feature of the Big Bang theory. Inflation appears to be here to stay, even if the precise mechanism of inflation remains unknown and worrisomely fine-tuned. We've reached the limit of our understanding, and there's a lot of uncertainty about whether our current explanations of the universe are correct. If the inflaton field's origin is unknown, how can one tell if its shape is unusual and fine-tuned rather than completely unsurprising? As we have seen, the phenomena do not wear such a label on their sleeves. What is merely coincidental in one physical theory becomes the typical case in another, and where the physics itself is unclear, judgments about how likely or unlikely a phenomenon is also becomes unclear. And this problem is exacerbated when certain natural constants are considered. Just as the overall history and shape of the visible universe depend upon special initial conditions in the original Big Bang model, many of the most general features of the visible universe depend quite sensitively on the precise values of various constants of nature. These include fundamental particle masses, quarks, electrons, neutrinos, and so on, as well as physical parameters such as the fine structure constant, which reflects the relative strength of various forces. Some physicists argue that if the values of these constants were even slightly different, the structure of the universe would have changed dramatically. Because the down quark is slightly heavier than the up quark, the proton is slightly lighter than the neutron, and because the proton is lighter than the neutron, a proton cannot decay into a neutron and a positron. Proton decay has never been observed, despite extensive experimental efforts. However, if the proton was sufficiently heavier than the neutron, protons would become unstable, and chemistry as we know it would be forever altered. Similarly, it has been claimed that if the fine structure constant, which describes the strength of the electromagnetic interaction, differed by only 4%, stellar fusion would not produce carbon. Carbon-based life forms could not exist in the absence of an abundance of carbon. This is yet another way in which life as we know it may appear to be highly contingent. We would not be here if the constants of nature had slightly different values. The specifics of these calculations should be treated with caution. It may appear to be a simple mathematical question to determine the consequences of twiddling a natural constant, but consider the enormous intellectual effort required to determine the physical consequences of the actual values of these constants. No one could sit down and rigorously work out an entirely new physics in a weekend. Even if we accept the main conclusion that many of the universe's most widespread structures, as well as many of the more detailed physical structures that support living things, are sensitive to the values of these constants, what happens next? Some physicists simply feel that the existence of stars and planets and life ought not to require so much luck. They would prefer a physical theory that predicts the emergence of these structures as a typical and robust phenomenon rather than a lucky roll of the cosmic dice that determines the constant values. Of course, the metaphor of a cosmic dice roll is unfortunate. If a constant of nature truly is a fixed value, it was not the result of any random process. It is not at all clear what it means to say in this context that the particular values that obtain were improbable or unlikely. So what options for explanation do we have if we believe that the presence of abundant carbon in the universe does not necessitate a unique and previously unexplained set of values for nature's constants? We have seen how altering the Big Bang's basic dynamics can make some phenomena much less sensitive to the initial conditions, making them appear typical rather than exceptional. Could any type of physics explain the values of the constants of nature in the same way? To counter the charge that an outcome is improbable, increase the number of possible outcomes. The chance that any particular sperm will find an egg is small, but a large number of sperm overcomes this low individual chance, resulting in offspring being produced on a regular basis. The likelihood of a monkey writing Hamlet by randomly pressing keys on a typewriter is negligible, but given enough monkeys and typewriters, the hypothetical probability of producing a copy of the play approaches 100%. Similarly, even if the constants of nature must fall within a narrow range of values for carbon to be produced, making enough random choices of values may yield special values. But given that the constants of nature are said to be constant, how can there be so many different options? String theory offers one possibility. According to it, space-time has more dimensions than are immediately visible, and these extra dimensions beyond 4 are compacted or curled up at the microscopic scale, forming a Calabi-Yau manifold. The natural constants are then shown to be dependent on the precise form of compactification. There are hundreds of thousands, if not infinitely many, distinct Calabi-Yau manifolds, and thus many ways for the constants of nature to emerge. If there is a mechanism for realizing all of these possibilities, it is likely that at least one will correspond to the values we observe. One inflation theory, known as eternal inflation, proposes a mechanism that would lead to all possible manifolds. According to this theory, which was first proposed by cosmologists Andre Linde at Stanford and Alexander Vilenkin at Tufts,
you could think that it's impossible for the universe originate out of the state with no universe simply because of energy conservation.
The universe is much, much larger and more exotic than the visible universe we are aware of. The vast majority of this universe is constantly in a state of hyper-exponential inflation, similar to the inflationary phase of the new Big Bang models. Within this expanding region, bubbles of slowly expanding space-time form at random, and each bubble is associated with a different Calabi-Yau compactification and thus with different natural constants. Given enough tries, just the right combination of monkeys and typewriters will emerge, so it's no surprise that life-friendly universes like ours exist, and it's also no surprise that living creatures like ourselves would live in one. Now, there is one more conceptual possibility for overcoming fine-tuning that is worth considering, even though there is no explicit physics to back it up just yet. In this scenario, the universe's dynamics do not aim at any particular outcome, nor does it randomly test all possibilities, but it still tends to produce worlds in which physical quantities appear to be adjusted to one another. This type of physical process is referred to as homeostasis. Here's a simple example. When a large object begins to fall through the atmosphere, it is initially accelerated downward by gravity. As it falls faster, the air resistance increases, which counteracts the gravitational force. When the object reaches a terminal velocity at which the drag equals the force of gravity, the acceleration ceases and the object falls at a constant speed. Assume that intelligent creatures evolved on such a falling object after it reached its terminal velocity. They develop a gravity theory that allows them to calculate the net gravitational force on their falling home. In order to determine the mass of an object, the exact composition of the object must be determined throughout its entire volume. They also develop a drag theory. The amount of drag produced by a portion of the object's surface would be determined by its precise shape. The smoother the surface, the less drag. Because the object is falling at a constant rate, the physics of these creatures would include a constant of nature that relates surface shapes to forces. To calculate the total drag on the object, the creatures would have to carefully map the entire shape of the surface and use their natural constant. After completing these difficult tasks, our creatures would discover an amazing coincidence. The total gravitational force, which is a function of the object's volume and composition, almost exactly matches the total drag, which is a function of the surface shape. It appears to be an example of incredible fine-tuning. The data used in one calculation has nothing to do with the data used in the other, yet the results match. Change the composition without changing the surface shape, or the surface shape without changing the composition, and the two values will no longer be nearly equal. But this miraculous coincidence would be anything but. The problem is that these creatures would regard the velocity of the falling object as a natural constant. After all, it had been a constant for as long as they have existed, even though it is a variable quantity. When the object began to fall, the drag was not balanced by gravity. As a result, the object accelerated, increasing velocity and thus drag, until the two forces were balanced. Similarly, imagine discovering that some of the quantities we consider constants are not only variables between bubbles, but also variables within bubbles. These variables could naturally evolve to stasis given the right set of opposing forces, and thus appear later as natural constants. And stasis is a state in which several independent quantities have become fine-tuned to one another. The issue of cosmological fine-tuning is never simple. It is not clear in the first place when it is legitimate to complain that a physical theory treats some phenomenon as a highly contingent product of chance. If the complaint is valid, the cosmologists have several options for resolving it. The inflationary Big Bang shows how a change in dynamics can transform delicate reliance on initial conditions into robust independence from the initial state. The bubble universe scenario demonstrates how to overcome low individual probabilities by multiplying the number of chances, and homeostasis provides a mechanism for variable quantities to naturally evolve to special, unchanging values that could easily be misinterpreted as natural constants. However, our modern understanding of cosmology reduces many facts of central importance to humans, particularly our species' very existence, to mere cosmic accident. None of the methods for overcoming fine-tuning offer any hope of reversing that realization. In the end, we may have to accept that we are just another accident in an accidental universe. Now, if the corner of the universe that we occupy is so finely tuned for our existence, What says the same conditions cannot be replicated in other parts of the universe and support life, whether life like we know it or otherwise? Are we simply special to be in the exact location for things to work out, or just fortunate? And what are the chances of the same conditions being enjoyed in a distant part of our universe? That is where another interesting theory comes in that postulates the existence of similar worlds to ours. The multiverse theory proposes that the vast region of space known as the universe is not the only thing that exists. Even if our visible universes, stars and galaxies stretch into infinity, there are theories that other universes may exist in parallel dimensions, or that the vast region of our own universe is one of many such cosmic expanses. If there is a multiverse, everything that exists is made up of many universes that can be thought of as alternate realities, parallel universes, multiple timelines, and many worlds interpretations. What is the multiverse theory and how does it work? A model of multiple universes could be created in a variety of ways. Our own observable universe could exist in a region of space or bubble of which there are many, or parallel universes could exist on different timelines. There is also the possibility of higher dimensions in which many three-dimensional universes like ours could coexist in an n-dimensional universe matrix. Max Tegmark's theory has a well-known scheme for classifying multiverses into 4 levels, with higher levels expanding upon lower-level universes. According to the theory, the first level of other universes simply extends beyond the range of our visible universe. Second-level universes exist beyond our own bubble of galaxies, separated from our universe by vast regions of space devoid of galaxies or stars. Prior to the 1930s, it was thought that our Milky Way was an entire universe, and other galaxies were referred to as island universes by some scientists. Level 3 universes, like our own, are three-dimensional, but they split off from other universes through quantum interactions to form an infinitely branching multiverse. Tegmark defines the 4th level as an all-encompassing theory of everything that exists, implying that all multiverse theories and various types of parallel universes must reside in some way within this 4th, totally infinite collection of universes. The concept of multiple universes can be traced back to ancient Greece. The Greek philosophy of atomism contained the first recorded example of a theory of multiple worlds. Although science did not confirm the existence of the atom for many centuries after the time of ancient Greece, some scholars at the time believed that all matter was made up of tiny invisible particles called atoms. Collisions of these particles, according to this theory, would create new worlds. Another ancient philosophical idea proposed by the philosopher Chrysippus proposed that the universe most likely ends and is recreated, implying an infinite number of universes that exist in the past and future. The term multiverse was coined by the American philosopher and psychologist William James in 1895. It was not, however, used to denote multiple worlds or universes. The term in this context referred to a variety of interpretations of natural phenomena. It wasn't until the late 20th century that mathematicians and physicists began to believe that multiverse theories could provide a better explanation for quantum theory and explain the origin of our own universe prior to the event known as the Big Bang, when our universe began to rapidly expand from a very small, dense point to the vast cosmos we see today. Brian Greene, a physicist and science popularizer, proposed the many worlds theory as an example of a modern multiverse theory. Although the concept of parallel universes has a fictional ring to it for most people, it appears to be gaining traction among theoretical physicists. Some of them believe it's a plausible explanation for subatomic particle behavior. According to multiverse theories such as Brian Greene's many worlds interpretation, the paradox of quantum particles can be elegantly explained by theories that describe them as branching off into different parallel universes. Greene, like Max Tegmark, has developed his own classification system for various types of multiverses. One example is that the definition of a never-ending continuum of possibilities causes any possibility to occur due to the nature of infinity. This type of multiverse is known as a quilted multiverse. Green also describes a popular multiverse model known as a brane. The brane exists on a higher dimension where vast multitudes of membranes from different dimensions collide to form three-dimensional universes like ours. This theory is used in string theories, which use higher dimensions to explain reality's structure. There is also the black hole multiverse. Physicists are still unsure about what happens to objects that perish within a black hole. Because of what happens to stars and other objects that are drawn into them, some scientists believe that our universe could have emerged from the other side of a black hole in a parallel universe, and that there are a vast number of such universes that have been spawned by black holes. And string theory has given rise to several multiverse theories to explain the strange behaviors of quantum particles that teleport instantly, entangle with other particles despite vast distances between them, and even exist in more than one state or location at the same time, posing a paradox that mathematicians have struggled to validate. M-theory is a popular interpretation of string theory in which the most fundamental constituents of reality are described as one-dimensional loops that vibrate at different frequencies that define their nature and function within the fabric of reality. M-theory and string theory are both attempts to provide a single theory that integrates the physics of the observable macro world with quantum physics micro world. String theory and M-theory both postulate dimensions other than the three we interact with and observe, namely height, width, and length. The mathematics of quantum theory has been found to work better within models of reality comprised of 10 or more spatial dimensions, in addition to 1 or more time dimensions, leading to increased support for additional dimensions. Let's hear what you think of how the universe is just perfect for us in the comments section below.